Okay, so let's just start now. I guess anyone that wants to join will join in the next few minutes. So welcome, and the recording is also available. Welcome again to our Cairo class. This is the 6th week, and today we'll be having Alex from the StarkNet team to talk about layer 1 to layer 2 messaging bridge on StarkNet. So Alex, it's good to have you here.
Yeah, thank you. Thank you. Good to be here.
Welcome, Alex.
So, thank you. Okay, yeah, so let's start. I'll first start with some slides. We'll go over, maybe let's start sharing the screen and can start chatting. Yeah, so I'm Alex. I work at Starkware, and today we'll talk about the L1, L2 bridging capabilities, or more correctly to say messaging capabilities, because in this case we are doing something that is not just a bridge. And then later we'll see some code on how to implement it, some examples, maybe talk about some examples that exist elsewhere on some repositories. Yeah, and questions, I guess, will not a lot of people. So like if you have a question, then ask and I'll try to answer. So there are many bridges out there between L1s and L1s and L1s and L2s. Usually these bridges are meant for transferring tokens or NFTs. Sometimes they work as part of the protocol, or sometimes it is an external DApp or something like that can incentivize people to put liquidity on both sides, and that's how they can transfer funds. But those applications, those bridges are indeed usually limited to just transferring funds. Now, this is nice and important. Obviously, if we are building a layer 2 or just a cross-chain world, then transferring funds is probably the first thing that we're going to want and do. But if we're building a messaging system that is more complex and not complex, but more flexible, that allows us to send anything between our L1 and L2, then we can do same things that perhaps are not possible with just transferring funds. And later we will see some examples and some code. So obviously I don't need to get into what StarkNet is. This is a 6th week, so you probably already know about that it's the layer 2 and it's a validity rollup, etc., etc. So yeah, so we'll focus on the messaging. So things that we can do when we have messaging that is more flexible is execute any type of logic, both on the L1 side, on the L2 side, and it doesn't have to be just a withdraw and a mint. And this opens up this space to a whole lot of new applications, new ways to think about what can we do with bridges, what is possible, and build new protocols on top of that. Great. So next we'll talk about how this works on the technical side, like what happens when you want to send message from StarkNet to Ethereum, see how it looks like on Explorer. And yeah, so the flow more or less is this picture. You might have already seen it. And I'll go over it briefly, and then we'll go into the details. So it starts with someone on L2 sending a message to their DApp. This is the one here. The DApp will probably have some function or some call that will initiate the call, send message to L1. This send message to L1 will have parameters of who is the receiver on L1 and the payload of the message. It will then be included in the block by the StarkNet OS and sent to the verifier. The verifier. Sorry? I don't understand.
Yeah, I guess just a mistake. Just continue, please. Just continue.
Sorry. Okay. It is sent to the prover to prove the state transition as with any other block, and it is also sent as a part of the state update and eventually consumed. Now let's dive a bit deeper into the details and understand each step of this diagram. So you're interacting with the DApp on L2, for example, the bridge in this case, with the wallet. Let's say you are initiating a withdrawal, and this will create, first of all, a transaction on L2, and it will get sent to a block. Now, the DApp on L2, this is an example code from the bridge, will somewhere have this last line here that says send message to L1. So this is a call to something that you need to import, and you make a call to this function, and it receives some parameters. First of all, the address on L1 where this message is going to be sent, and then you're going to create the payload, like as you can see here, an array of fields, basically, and when you call the message, you will also specify the payload size. This is executed as a regular transaction, nothing special about it when you're doing it on the L2 side, and now it is going to be included in a block. Once it is included in a block, you can get an update. You can see it on a block explorer that it was sent on L2, and there is some hash of the message that is a function of the payload and the receiver. And this hash is what we're going to follow with this message as it progresses through our diagram. So yeah, in this case, it is a withdrawal, so there are more internal calls. There is, because we're using the account abstraction here, so it calls the execute, calls the withdraw, calls the burn, but it is not actually that relevant for us now. Okay, now what's happening on the L1 side? On the L1 side, we have this component that's called the StarkNet core contract. And this is basically the contract that lives on L1, and this is where all the updates about what happens on StarkNet arrive. So all the state updates are going to this contract. The old state, the new state, all the state diffs, all the storage that is being sent to L1 as call data. And in addition, we have the messages. So all of the messages that were sent to L2, they are registered on this contract. And also there is an event that is emitted and lets us know that the message has reached L1 and it is now ready to be consumed. The prover has executed the block which included this message. All of the state changes that were part of the transaction happened and are being proved. So once this state transition reaches L1, we can be sure that this message has happened on L2. Okay, so what happens on an addition? Okay, one more thing is that on the L1 side, we increment a counter. Basically, we take the hash of this message on L1, similarly to how we computed the hash on L2. And we increment a counter that says, okay, there is a new message here that lives on L1. that is ready to be consumed. And only if you provide this data on L1 as well, can you consume it. Questions so far on this? Before we consume the message? Okay. Okay, so when we are interacting from L2 to L1, we're doing it in 2 steps. On the L2 side, we sent a transaction and it is just like any other transaction. But on L1, the transaction is not executed automatically. It needs to be consumed by, it can be consumed by whoever, but usually, but only by the contract that it was sent to. But anyone can send the message to initiate the consumption unless the contract states otherwise. So this consume message from L2, this is a function that is part of the core contract. And this is what we call from a contract that lives on L1, for example, the bridge, when we want to consume this message. What do we need to provide? We need to provide the from address, which is whoever sent it on the L2 side, which is the DAP that sent it. This comes pre-programmed, so there is no way to fake who is the sender of the message. And the call data, which is which is similar to what we configured when we send the message on L2. We compute the hash similarly in the same way, and only if the same hash exists as part of the registry on the core contract, can we decrement the counter and mark the message as consumed. Make sense so far? Any thoughts, questions? Like this is sometimes a bit tricky to understand. No, everything is good. Everything's understood. Okay. No one is talking, so I'm not sure if if you can hear me.
Yeah, well, we can hear you.
Yeah. Okay.
Yeah, you can actually hear you.
Okay, fantastic. Okay, so let's look at an example of this. So StarkScan is a great explorer. It shows, among other things, all the things that that happen with a message. So we can go to a message here and filter by its type. It says also the direction. So these are messages that went from L2 to L1, like we just discussed. You can see here that it went through all the stages. It was sent on L2, attached on L1, which means that the proof has reached L1, and all the information about this message, or basically its hash, has been registered on L1, and eventually it was consumed. So we can also take a look at things that happened here. So this was a transaction, probably a withdraw. Yeah, we can see it was a withdraw on the bridge. Specified the amounts, the L1 recipient. Next, we can see the logs of all of the messages that were either registered or cleared on the StarkNet contract alongside with this one. So when we send the proof, the messages that we want to add to the contract, the ones that are going from L2 to L1 are added. We can also see this state update happening on Etherscan. Yeah, there it's state update, has a bunch of call data of many other things that are also happening, and this in particular, and all the other messages the other way that were cleared. And eventually, in this case, the person who withdrew their funds also also withdrew them on L1. Yeah, as usually link here. Yeah, so they also withdrew them on L1, and this is where they transfer it to their contract on L1. So just to recap, we'll go back to the slides. The message is first sent on L2, registered by the OS, then updated in the core contract along with other proofs and state updates that happen when we update the state. Also checks that the block was indeed proven correctly by the verifier. And then in however time the person who sent it can come and consume it. It is not sitting there for any limited time. It is stored on a hash map on the core contract, and then you need to provide the correct information, which is the same information you set on L2, to consume the message on L1. So in this case, it is a two-step process. This process can sometimes take some time, because in this case, we need to wait for the proof before we can consume the message on L1. So this can be half an hour or a couple of hours on testnet, and it can be longer than that, 8 hours on mainnet, for example. So it sometimes is a bit tricky to debug this, but relatively to other layer 2s, where sending messages like this can take weeks before it is finalized on L1. So here it is just a few hours. And there are also tools to debug this and build this locally on the DevNet and the local Ethereum node to build the tests and test your application. Good so far? Okay, then. So a bit about the other direction. So here we're going to do something that is very similar, but slightly different. So unsurprisingly now, the message starts from the L1 side. The L1 contract will have some endpoint that will send and register the message on the StarkNet contract. Once that happens, the sequencer notices this log, notices this message, waits some time for the block to be finalized, and then again includes it in a block. The message will have a destination on L2, and this destination contract should have a special function that's called an L1 handler. And this L1 handler will be executed again, just like any other code. And once this execution is done, that's it. The execution is done on the L2 side, just like any transaction that is executed. And now waiting for the proof is just, again, waiting for the final state update, the final confirmation when all of the information is updated on L1 and the state is updated and proved. But for all intents and purposes, it is considered as an executed transaction. So we'll go a bit over the details again. So this is again the function on the L1 contract, the core contract. So you can see it receives the to address. This is the address on L2 that is going to receive this message. it receives a selector. The selector is the name of the L1 handler on the L2 side that we are going to call, and call data, which can be, again, any payload, any size, and any configuration that we want, that again will be sent to L2, and there we can do whatever we want with it. And again, we increment the counter here to indicate that this message has been sent, but it has not yet been processed by L2 and proven on L1 again. So this is an example of the L1 handler. So again, once it reaches L2, it is executed by the sequencer and included in a block. The handler receives a from address, which is again the contract that sent it on the L1 side, and other information that could be interesting. And that's it, and it executes the code. So this L1 handler can only be called if the parameters were passed correctly. And here you can put whatever logic you want here, make sure that the user has enough balance, or whatever. Do any logic execution that you want based on the call data that was passed. So this obviously requires a correct code on both ends, both on the L1 and the L2. You don't want to any of the sides to be able to, for example, make infinite mints or infinite burns or anything like that. So there is more importance for the developer to know what they're doing on both sides here. So again, the L1 handler is executed, included in the block, and now the OS is going to execute it like in any other transaction. The state updates that followed this execution are added to the batch that is going to be sent to the core contract as part of the state updates. And the proof is going to be verified by the prover. And once all of this happens and the proof is executed on L1, we can consider the message handled, and we decrement the counter that we initially set to 1 on L1. Yes, the question I see.
Yeah, there are some questions in the chat. Probably just open the chat.
Okay. Yeah. Okay. Yes. So I'll open the chat. Perfect. How do I see the chat? Yeah, just a second. Okay.
Yeah, it's down below.
Why is the process so slow? The process, you mean of how long it takes for a proof to reach L1? I assume. So generating proofs is something that takes time, and also the cost is the highest cost of the whole process is basically the data on the L1 and the execution. So it is a balance. Once there are more users to StarkNet and the blocks get filled up quicker, there will be enough demand to send these blocks faster to L1. But part of the reason that StarkNet scales is that the more transactions are executed on L2, the cheaper it is per transaction on L1. So there is a balance here of we want there to be enough transactions that it will make sense to amortize the cost and only execute one verification on L1, which can be costly. Okay. The questions of difference between sending L1 tokens or NFT, send L2 to L1. Okay, so about tokens and NFTs. So on the official StarkGate bridge, currently you can send only tokens. On an application that you build yourself that can also be a bridge, for example, for NFTs, you can do whatever you want, right? You can send data that represents an NFT or a token or just instructions or whatever you want. So at the end of the day, there is no difference. It's just data being sent between the networks. It can represent anything. About how long does it take L1 to L2 or L2 to L1? So the L2 to L1 direction is the one that takes longer, because there you need to actually wait for the proof to reach L1. This is the long process, the slow process that was mentioned before, where we amortize all of the information and only then send it to L1. The direction from L1 to L2 is much shorter, because there only the sequencer only needs to wait for enough confirmations on the block on L1, and it can already be sent on L2. Also in this direction, you don't need to make any other action. So the sequencer is executing the transaction, calling the L1 handler. Yeah, there is no second stage operation, just the L1 handler is going to be executed, and after some time it will be proved. Great, thanks for the questions. Okay, yeah, so just again wanted to quickly show this how it looks like on the Explorer. So again, we can see here, filter here, but messages that were cleared on L1. So it was, this actually happens first, right? It is registered on L1. Sorry for the, just a second. Yeah, sorry. So
yeah,
I
I don't know if you can enlarge the screen a little bit more.
Sorry, can I what?
Can you like your screen, can you like make it a little bit big?
The which part?
The stack scan, okay, yeah, I mean it's okay now. I think it's kind of okay now.
Okay, like this.
Yeah.
Okay, good. Okay, so this is a deposit. Someone is depositing, again, this can, in this case, it is to the StarkGate bridge, but this can be any contract on L1. It doesn't have to be the bridge. Bridge is just, I guess, the most popular contract that is being called. So when it is registered on L1, there's a log there that says there was a message to L2. But all it does is call the contract, the core contract, and add a filter that there is a new message that is going to be, it needs to be consumed. This happens automatically. The consumption on L2. So this is the sequencer. It just calls the handle deposit L1 handle, and funds are transferred to the address that was specified. So this again is much faster than the other direction, and you can see this is like 31. So this is like 3 minutes after that. And the cleared on L1, this can happen much later. This is when the proof is actually sent to L1 and the state is updated. But for the user on L2, it doesn't really need to bother him. The state is already updated. They can start doing whatever they want and use the funds or use the application, etc. Okay, any other questions on this direction? I'll open the chat again. Okay, cool. Yeah, so why is this cool? We touched upon it briefly. One of the cool parts is that there is no additional trust that is being added by this messaging system besides the one that is already how StarkNet works. So if you trust the validity rollup, you trust the way that state is being updated and registered on L1, this is already part of the process of how messaging works. So there is no additional committee, there is no additional multi-sig or some hardware that needs to make sure that messages are being sent and processed. There is the core contract where messages get registered, and when a proof is sent, if the proof is valid, part of the process is also consuming and introducing new messages from L1 to L2 or vice versa. And another cool thing is, as we said, although it is relatively slow to send messages from L2 to L1, it is still orders of magnitude faster than on something like an optimistic rollup, where a system like this would mean that you need to wait for a week to pass any data from L2 to L1. So compared to that, a few hours sounds much faster. The thing that is really exciting about this whole new approach is that it really opens the possibilities for new things that can be done. So you can have a contract on L1 that's part of any transaction that is being called to it, will call the send message to L2, and something will happen on both N1 and L2 with just a few minutes apart. And you can build like contracts that control your account on L1 and L2 as well, or the other way around. You can send messages that deploy new contracts, and probably many other things that were much more limited in the things that you can do. So now you can build more complex logics on both sides, because now you can send any data for the execution. So these are the links. There are some links here to the docs on how the L1, L2 mechanism works. Some documentation there about some of the things that we discussed here. The StarkNet education team has built a great tutorial. Look up StarkNet edu on GitHub and the StarkNet messaging bridge. So if some of these things sounded a bit confusing, then it's a great way to try and getting a hands-on experience with doing them. And StarkScan that we already looked at a few times today. So this is the part of the presentation. Now we'll go over a bit of code. This is okay. So first of all, any questions so far about the messaging before we dive into some code on either direction? Or all clear, or nothing is? Okay.
Okay, so just one question. I mean, I know you talked about it, but I just wanted to like be a bit more clear. Like what differentiates let's say StarkGate bridge from let's say hop bridge that could be hacked or something. I know you mentioned in your slide that there's no funds in the bridge, rather it's just data. So this data can be hacked or something. Like what makes it like superior?
Okay, so there is still contracts on both sides that need to be written correctly for there to not be any hacks. It's not a system that's designed to prevent hacks. The difference, for example, is some networks have bridges that rely on something like SGX to do the bridging. So you send funds basically to some EOA on Ethereum, and there is a system that you don't really have any knowledge about that is running in the background on the backend and sees funds coming in and executes code on SGX that, for example, can be problematic. There were some few problems with it were disclosed last week. And this SGX that now issues the transaction to either create funds for you on L2 or withdraw funds for L1. So if this SGX gets hacked, this is something that can completely drain the bridge of any funds, right? So it is a physical attack, and the same thing for bridges that are operated by multisigs, which also happened before. So if you have a bridge that basically operates as a multisig contract, and a few people or a few machines need to sign a 3 out of 4 signature for new funds to be bridged, and all of these keys are compromised, then again the bridge can be drained of funds, and this has nothing to do with how perhaps security works on the protocol. It could be whatever consensus on both sides, and it doesn't even matter because there is some additional party, multisig or hardware, that is responsible for how the bridge works. Here it is actually part of the protocol. Here it is actually part of how the system operates. So every state update the state changes that happened on L2. So this is all transparent and is forwarded to L1 with any state update anyway. And part of it is also the messages that are sent to and from L1. So if you build a good bridge with good code, if you trust the system to work, if you trust that StarkNet is going to advance and get to a new state, then you can also trust that the messages are going to be passed and consumed correctly. Make sense?
Yeah, thanks.
Cool. Yeah, cool. Exactly, yeah. So if there is a new proof and it had your message in it, then it will arrive on L1. You don't need to fear that the multisig will not see your message or something like that. Yeah, cool. So yeah, buggy code can be buggy on any system. All right, so it's so we'll go over this this bit of code. It is actually a proposal that I've made on the community forum. Basically, the idea is that in most systems there is that a token, for example, that first exists on L1, let's say USDC, and now when you want to bridge it to L2, you need to deploy a new contract on L2, talk to someone and say, this is me, this is I who own the contract on L1. I have deployed this contract on L2 now, and please register somewhere that this token on L2 is the legitimate token on L1. So nobody can come up with their own USDC on StarkNet. So this is the process that works for many bridges. Some of them is a bit more automated, some of it is less, but usually it starts with the token on L1. So what if we want to create a token on L2 and don't have to go through the process of even understanding Solidity or even knowing how to deploy a contract on L1, but we still want to have the option to deploy it to L1 sometime because whatever, we want to bridge it to somewhere else. We want to bridge it to another network or to another rollup, or just want to create an L1 presence for this token. And it already only exists on L2. So the idea here is that there will be a bridge that instead of receiving L1 tokens and locking them up, it can receive a message from L2, and if there is no token that exists no contract that exists for this token on L1, it will deploy a new contract, a new ERC20, that will only be accessible by the bridge. Only the bridge will have options to mint and burn tokens on this instance on L1. And even tokens that didn't have an L1 presence, didn't start their L1 life on L1, will now have a contract deployed. So that's the idea. I know you looked at the code before, so I guess we can look at this code as well a bit. So on the L2 side, the ERC20 that I want to use, it needs to implement this this interface, which is called bridgeable. And it has three main functions. It has create an L1 instance, bridge tokens to L1, and the bridge tokens from L1. So let's see, for example, what happens in a create L1 instance. So again, this is like everyone is trading this token, everything is fine. And for some reason, I want to move some of my tokens to L1. So in this case, I don't have to ask permissions from anyone. I can be any user that can call this function to create an instance of the token on L1. The contract will have the bridge, the L1 bridge pre-configured. This will be hard-coded. And it will pass as data, as payload, the name and the symbol of the token. And the bridge will call the function send message to L1, which we are importing. This is a standard function. This is how you communicate with L1. And give it the information. Sorry, yeah, I'll increase that by a lot. Better? Yeah, so this is how we call the send message to L1, and we pass it the information. The to address is the bridge, the bridge which we are that is initiated when this bridgeable contract is born. So again, this can be hard-coded, so it can be completely trustless. And the payload is just the name and the symbol of the contract. we'll go over this function of the bridge tokens on L1 and then see how it looks like on the L1 side. So in this case, again, there is a caller, and the caller is the one who is going to. Sorry, actually, the caller is not that interesting here. There is an L1 recipient, right? We need to specify the L1 recipient, the address on Ethereum who is going to receive these funds. And again, so we are sending to the bridge the L1 recipient and the amount of tokens that are going to be received. And yeah, okay. This is just the interface. There is another part here that's why the caller is important, but it hasn't it's not written here. It's in the actual ERC20. So yeah, here the caller is important. So it calls the bridge tokens to L1, the function that we saw before, and in this case, it burns the tokens of the caller. So a message is being sent to L1, and the funds on L2 of the caller are being burned. Now let's see what happens on the L1 side. Yeah, so here we have a bridge, and the bridge is going to have similar functions to what we saw on the Cairo side, but in the other direction. So here we have yeah, not this one. Yeah, create L1's instance. So this is the function that we need to call once the message reaches L1 and we want to consume it. The information that we need to pass is the L2 address of the token, which is where we sent the original message from, and again, the token name and token symbol. And here, basically, this is where the magic happens. We make this payload, call this consume message from L2. We call it on the StarkNet core contract, which is hard-coded here, or whatever, initialized when we start the contract. And only if this message exists, then the message will be consumed. Otherwise, we will revert. If there is no contract that already exists, then we will call this create ERC20, and we will create a new contract for this token that hasn't existed before on L1, right? So this is like the cool part. We are not just moving tokens from side to side like we are used to with any regular bridge. Here there was no token on L1, and we sent a message that will deploy a new contract for us in a deterministic way. It will also have the name. It will be initiated with the token name and token symbol of the L2 contract. And again, this can be all done trustlessly and in a decentralized way. There is no governance, no control. This is just code calling code. For the consume message bridge tokens from L2, so this is when the contract already exists, and we're basically doing the same process. We're passing the token receiver, which was, can open up the bridgeable. So here we passed the L1 recipient. Here, this is the receiver. The amount, because it is UN256, it needs to be passed as two numbers, the low and high. So this is the split here, right? We receive an amount in UN256, needs to be split to this payload 1 and 2, which is respectively this low and high that we are passing in the L1 message. And again, consuming the message from the core contract, and only then, if this thing passes and does not revert, we will revert the message to the caller. So this is the we are minting the same token to the token receiver that we have specified, and the amount that we have specified on L1. Another nice thing about it is that in terms of supply, the supply is always the sum of both sides, so there is no locked amounts anywhere that can be drained. Either the user has it on L1 or the user has it on L2, right? There is no bridge, but doesn't mean that there can't be any bugs. This is not audited code. This is just an example. A bug in this code could enable someone to mint infinite tokens on both sides, which is just as problematic as draining the bridge. Okay, so one more important concept that I wanted to touch on. Okay, so now we want to bridge tokens to L2, sorry, from L1. So this is Solidity. This is Ethereum. We want to bridge tokens to L2. So some things we need to specify is the receiver, right? The address on L2 that is going to receive this message. And another important one is the selector. So on the ERC20 side, we have this L1 handler. This is the part that handles the received message from L1. This is what the sequencer is going to call. This is what's going to be called after the block is finalized, etc. All the things that we talked about. So this bridge from A1 selector, it is a constant that is defined here. It is this huge number, which is basically the hash of this string, right? So there are a few tools to do that. So you take the hash of the string bridge from L1, and it gives you this number in this case. And this is the selector that you need to pass, so the sequencer will know which of the L1 handlers to call, right? Because you can have more than one L1 handler on the L2 side on the same contract, right? It's not limited to one, and it's not this specific one. Many L1 handlers, they differentiate from one another by the selector, and the rest is passing the payload. So here, again, tokens are going to be burned on the L1 side. And after a few minutes, the handler is going to be executed. Here, again, similar process. We create the amount as a U into 56 from the low and high. As you can see here, the L1 handler already has all the fields separated, the recipient, the low, the high. So this is just in the same order that we passed them here, right? No need to do anything too fancy to unpack it, but maybe need to do some work to pack it correctly, break it all down to felts. And it calls the bridgeable token. This will this will not do much. It will make sure that the from address is indeed the address of the bridge, so that it doesn't. So you can't call this from any place. Only the bridge that is pre-configured is allowed to call this function, and only if this doesn't revert, then new tokens are minted for the user again on the L2 side. Okay, yeah, so that's it. Any more questions? Or when a token is sent to L1, is it burned in L2 and then minted in L1? Is this correct? I didn't understand this part. Yeah, so this is in case of this implementation. This is what happens. Yes. So here this is where you bridge tokens to L1 and they are burned. This is not like the official implementation. It's just an example of things that can be done that is not a regular bridge, not the way bridges must operate or anything like that. Like this is a design choice. In this case, the ERC20 of the caller is burned, and here on the from L2 side, new tokens are minted, right? So there is a mint for a burn here and a burn for a mint there, but it could have been tokens locked, tokens unlocked, tokens minted, tokens burned. Like you can do any function here, any logic that you want.
Yeah, it's okay. It's okay.
Yeah, exactly. Yeah. So yeah, it's nice if there is a discussion about it. I think we will push it forward as something more official, as an official proposal for others to implement. Yeah, like you said, the supply is exactly the same. It's exactly the sum of both sides of the chain. Yeah. Okay, cool. Yeah, this is, if you want to search for it, it's called the L2 L1 Standard Bridge Proposal on GitHub. It's not fully ready, but it can be an example to look at somewhere as another example for code that does that. There are other examples. There is the repository of snapshot called the SX Core. They are making voting from L1, voting on L1 through L2 logic. So again, there is a message and information that is being passed there from L1 to L2 that has nothing to do with bridging, it has to do with voting. There is Herodotus, they are making storage proofs. So also information that is being sent from L1 to L2, and L2 is used to make sure that indeed the storage was what it says, verifies that on L2, and basically anything can be done like with that, for example, voting again. Yeah, okay, so I had fun. Hoped, sorry, another question there. When you pass in 256 as two fields in two different payload messages, how you pack them back on L1? Yeah, so there was an example of this here. This is how I unpack them. And when you pack them, yeah, you need to split it, right? So you need to unsplit it and split it. Wait, sorry. How do you pack them back on L1, right? This is right. Okay. Yeah, exactly. So when I consume it on L1, I don't need to pack it. I just pass the 256, the uint 256. What I actually need to do is to split the uint that I sent on L2. So it's actually unpacking in both cases. Right, I need to, on L1 side, I need to recreate the same payload that I sent on L2 so that when I call a consume message, the hash will be the same. Yeah, so in both cases, I need to unpack it. If it's the custom function I wrote, I think I took it from there, but sorry, it's not this one, it's this one. Yeah, I think I saw it somewhere, but something like that. Yeah, it moves some bits and creates two 128 bit numbers from 1 UN to 56. Okay, cool. Great, yeah. So hope this was of value, and good luck with the rest of the program.
Yeah, thanks, man. Actually a very nice class you did here. And if there's any other question, like you can probably unmute and probably ask in the chats.
Yeah, there is obviously many community places where you can ask questions. You can ask on Discord. You can ask on Stack Overflow, on various Telegram groups. So yeah, but yeah, definitely one of the cooler things about StarkNet is this whole messaging paradigm, which is not something that really exists on any other platform, on any other L2, that you can so easily communicate any information.
Yeah. Okay. I want to ask the slide you used for this class. Please, can you probably share in our group, or maybe make it accessible so I can share in the group?
Sorry.
I mean, the slide you used for the class, is it shareable? Can you?
Yeah, I'll ask that. Yeah, probably I can share it. Yes, I'll make sure.
Okay, cool.
Like,
okay.
Okay.
Yeah. Okay, since there is no further question, thanks again for the class, Alex. And for sure, probably if there's any personal question, people can just tag you in our group, in our StarkNet Africa group. So you probably answer them there. And maybe in the future, if we need assistance, we can probably message you on Telegram as well.
Yeah.
Okay, cool.
Okay, cool. Great. Thank you.
Yeah.
Thank you.
Bye-bye.
Yeah, bye.